Hi, thanks for joining me today. I've got a fun set problem. Let A be a subset of the positive integers from 1 up to 2n, with the property that if A and B are distinct elements of A, then A does not divide B. We want to find the maximum possible size of A, and obviously this will depend on what n is. So just to give an example of what this set A could be, maybe if we have 1, 2, 3, 4, 5, 6, 7, 8, so this would be the case where n is 4, maybe A could be the set 2, 3, 7, because if I choose two different elements from here, one doesn't divide the other. However, with this set, I couldn't make it bigger by adding a 6, say, because if I did try and add 6 in, well, 3 divides 6. So that wouldn't work. Now, this isn't to say that this is of maximal size. We want to find the set A, which has maximum size. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so I claim that the answer to this problem is that A has to be of size at most n. So firstly, I'm going to prove that claim, and then just give an explicit example of a set or a subset of 1 up to 2n, which is of size n. Okay, but let me first show that if we have a set with this property, then it has to be of size at most n. And the way we're going to prove this is by contradiction. So we're going to suppose A has size bigger than this, and then we're going to lead to a contradiction here. Okay, so A, we're supposing it has this property and it has size at least n plus 1. Okay, then what we're going to do is take every single element in our set A and write them in a special way. And I don't know if there's a name for this, but this is commonly used, where we're going to write every number x in our set A in the form 2 to the power of some number, which will obviously depend on what x is, times an odd number, which I'll call v here. So v is going to be an odd integer. So just to give an example here, let's imagine 140 was in our set. We can write 140 as 2 squared times 35. And 35 here would be that odd integer here. So you're basically stripping out as many powers of 2's as you can until you're left with an odd integer. Okay, cool. So we're going to write all of the numbers in A in this form. And then what we're going to do is just write down some boxes here. So V1, V2, V3, and so on here. And V1 is going to be the first odd integer, so that's 1. V2 is going to be the second odd integer, which is 3. V3, the third odd integer, 5, and so on. And we're going to go up all the way up to Vn, so the nth odd integer, which would be 2n minus 1. Okay, and now what we're going to do is look at our elements in our set A, and we've written them in this form. And what we're going to do is place them into the corresponding kind of groups. So if that's a box, that's a box, that's a box, and so on. Obviously, maybe we'd have a 35 in here somewhere. And so that would be what, V18, I think, the 18th odd integer. And so if we had 140 in our set, we'd write 140 here. If we had the number, let's go 12. So 12 is 2 squared times 3, so the odd integer part of that is 3. I'd put the number 12 in this box. Okay, and so we're going to go through all of the elements in A and put them in one of these boxes. Now, how do I know that every single element of A will be in one of these boxes, and I won't need to go to the next odd integer or some other odd integer? Well, every element in A has size at most 2n. And so the biggest kind of odd number that could be a factor of it is 2n minus 1. It can't have any bigger factors there. So 2n minus 1 is the biggest odd factor. And so therefore we can put all of these numbers in our set A into one of these n boxes here. Now, here's where the interesting thing arises. We're assuming that A has size at least n plus 1. And well, we've got exactly n boxes here. And so therefore, by the pigeonhole principle, at least one of these boxes must have 2 numbers in. So just to go over that, we have n of these boxes here because there are n odd integers less than 2n. But because A has at least n plus 1 elements, one of these boxes, we don't know which, is going to have at least 2 elements in it. It could have 3, it could have 4, but it has at least 2 in. So to put that mathematically is there exists some number some number I between 1 and n such that Vi, or there's two boxes, at least two elements in the box Vi. Okay, so therefore there's some number 2 to the k1 or ka Vi, and some other number 2 to the kb Vi, and both of these numbers here are elements in A. But here's the issue. One of these numbers must be bigger than the other, and that just is dependent on whether Ka is bigger than Kb, or which one's bigger out of these two. Let's just say, without loss of generality, Kb is bigger than Ka, and so therefore this one is bigger, so the bottom one is bigger than the top one. But then the issue is, this number here is very clearly a multiple of this one. It's just a power of 2 times bigger. But this contradicts this property that A has, and we've arrived at a contradiction. And so therefore A cannot have size at least n plus 1, and so therefore our claim that A has size at most n is therefore proved. So we've proved, using the pigeonhole principle, that A must have size at most n. And now I'm just going to show you that we can construct a set, subset A of size n that works, and we can actually think about this thing here. We need to basically make sure we put exactly one element in each of these boxes, and so by thinking about that, we can just use the set A being n plus 1, n plus 2, n plus 3, and so on, all the way up to 2n. Because these guys here clearly can't be multiples of one another, because even if you chose this guy and this guy, n plus 1 is bigger than a half times 2n. And so therefore, the only way you could be a multiple is if you're at least 2 times as big. But this 2n is not even as 2 times as big as this. So this guy here has size n, and we have proved that we can find one of size n. And therefore, the biggest possible subset with this property has size n. I hope you have enjoyed this video. It's a pretty nice problem and a pretty cool application of the pigeonhole principle here. Thank you for watching. If you are new to the channel, please do consider subscribing and giving this video a thumbs up as well. If you made it to the end, hopefully that means you've enjoyed it. Anyway, I'm going to stop waffling. Thank you for watching. I'll catch you in the next one. Have a great day.